We're going to continue with solubility and get into the solubility rules here a little bit more. There's a medical application here, and I'll warn you, those of you who are squeamish should look away right now or fast forward just a few seconds because there's that gross picture there of people having too much stuff dissolved in them, in this case, gout. Anyway, moving on here. Solubility is the maximum amount of a solute that can dissolve in an amount of a solvent. It is temperature sensitive. For most substances, they will become more soluble, specifically solids become more soluble with an increase in temperature, whereas gases become less soluble with an increase of temperature. And amount over here for reading that as a graph. Most commonly for solubility, it is grams of solute per 100 grams of water. From there, if we have less than that amount, we call it unsaturated, and we could still dissolve more in it. If it has that much, we call it saturated, and it contains the maximum amount of that. If you add more stuff and try to get it to dissolve, it's going to settle to the bottom of the container. And just like we mentioned with the weak electrolytes, how you can end up with pieces breaking down and other pieces recombining, you end up with the same thing here. So the individual ions that are dissolved are changing as some new ones dissolve and some new ones recrystallize, but you end up with what's called a equilibrium situation here, where the amount of stuff that is dissolved stays the same, but which pieces individually are there don't stay the same. Now, there is such a thing as a supersaturated solution where you have more dissolved in it than what you can, and you may be saying, wait a second, how does that happen? How can you get more in there than what's supposed to be in there? Well, we take advantage of that temperature dependence. So you have a substance that you can dissolve a certain amount at room temperature. Let's say you heat it up and you dissolve more of it, and then if you cool it very slowly and very gently, it will still have that more amount later on when it gets cooled back to room temperature. Now, it's unstable, and usually adding a nucleation site or jostling it, it will then undissolve rapidly in what we call crashing out of solution, and it will recrystallize, much like down here. Sometimes you can even get the whole thing to recrystallize depending on which solute you're looking at and how much solvent was needed there to begin with. I don't love this question here. Salt disappears when put in water. That would be unsaturated, I suppose. Having said that, you could take that right up to the saturation point and it would still be disappearing, but I understand what they're trying to say here, that if you add a little bit and it disappears, or appears to disappear, I should say, because keep in mind, it's salt water. The salt's still there, still tastes salty. But if you continue to add some and it continues to disappear, it's unsaturated. And if you're adding sugar here to water, but it doesn't disappear, then it is saturated. And I was very guilty of this as a kid, of just saturating my solution, Kool-Aid, or whatever drink it was, and just adding sugar, tea, just add a ton of sugar to it, and then you could not get it to dissolve because it was saturated. You dissolved the maximum amount that was in there, and you couldn't get more to dissolve, and yet I just kept adding it in, and then I just had wet sugar at the bottom. Also, unlike salt, sugar is not very soluble in water, and so you can't get as much of it to dissolve to begin with. And so that was always a limiting factor as well. It's why sugar dissolves better in things like hot tea, hot coffee, hot cocoa, and then you can let it cool down. If you don't get it saturated, it's not going to be super saturated as it cools down. I did go to Japan. I had the fortune of doing that, and they, at one restaurant, they brought out what looked like test tubes of liquid in there, and they had different liquids you could add to your tea, but they told me that this one here is sugar water, but it was super saturated sugar water, and so you could pour that in there and it's just super concentrate. Because it was already pre-dissolved, when you poured it into the other one, it was like they were just mixing. It was technically a solubility process where it was dissolving, but it was pre-dissolved in the test tube, and then you're kind of just watering it down when you dissolved it in your tea. And we'll actually get into that watering down, what's called dilution calculations, here in a few sections. Here they give us a specific data point that at 40 degrees Celsius, calcium bromide, we can dissolve 80 grams in 100 grams of water. And so if we only have 60 grams in there, then we are unsaturated. If we have 200 grams of potassium bromide that we add to the 200 grams of water. Well, we can handle this two ways. We can either figure out how much it is in 100 grams of water, and so then that would be 100 grams, which is going to be saturated. The other way that you could figure it out is you could say, okay, if I've doubled the amount of water here, then I double that 80 that we could have, and we could fit 160, and the 160 is less than the 200 there. To be clear here, this means there's going to be 40 grams settled out on the bottom. The last one here, 25 grams and 50 grams, that's only 50% of it, so it's going to be unsaturated. I did a quick percentage in there and saw that this is 80% and 100. However, simpler is probably just to double this one to 100 grams and then double this one to the 50 grams, and you can see that 50 grams is less than that 80 grams there. This here is solubility curves of different substances compared to their temperature. So here's the amount that can dissolve, and here is our temperature. You'll notice that most substances, the amount that dissolves increases. Now, how much dissolves for each of them is unique to the substance and can pretty much only be determined experimentally. You'll notice sodium chloride here barely goes up any. It's something like 38, 39 grams here at 0 degrees, and a whole 40 degrees over here at 100 degrees. But plenty of other substances really get more soluble. Potassium nitrate's one of the ones that has the biggest increase. There are a few exceptions to this where they become less soluble. There's a cesium compound that happens to become less soluble, I know. Another exception tends to be your gases, that gases tend to decrease, whereas the solids are increasing. Their solubility in water like that as well. A great example of this is your carbonation in pops or sodas, whatever term you prefer. The CO2 amount goes down as the temperature goes up. It's why warm pops go flatter quicker than cold pops. And that's actually what they give us here on this next one here, is why could a carbonated drink burst or explode if left out in the hot sun? Well, the CO2 that was in there in aqueous form is coming out in gas form now. And now that it's in gas form, the pressure is going to build up and eventually can burst. I had a can of Dr. Pepper I left in my car once, and it was a hot fall day, and I had a former student come in and tell me, I think something exploded in your car. And I went out there, and just the thing had shot up like a rocket. It had been in my cup holder, and I found it over on the floorboard, and it had literally just sprayed everything in Dr. Pepper. And then, of course, the water had evaporated away, and all the stuff that was dissolved in the water crystallized out or came out. It was more syrupy and just sticky everywhere. And I was very fortunate that my dad's telescope that was in the back did not get hit at all, but boy, was it a mess to clean up. And this one here, then, why do fish die if the water's too warm? The same thing happens with your oxygen, that your dissolved oxygen goes away. And neither one of those gases is all that soluble to begin with, but the increasing the temperature causes those gases to escape solution. In addition to temperature having an effect on solubility of gases, the solubility of a gas is also directly related to the pressure. And directly related means that as the pressure goes up, the solubility also goes up. And so you get more stuff dissolved under high pressure, and of course vice versa for low pressure. This is why beverages stay carbonated when they're pressurized, but then will go flat when they're depressurized, because carbon dioxide, being only weakly polar, does not interact with the water well, and so then it doesn't want to stay dissolved, but we can increase that. And that is called Henry's law. We've mentioned the solubility rules already, and some substances just aren't soluble. I'm not sure why we're repeating that chart, but there you go. And so it turns out that when you mix certain aqueous solutions, we get a reaction that produces an insoluble compound. For example, barium chloride, barium nitrate, etc. is soluble, but when you react it with, say, sodium sulfate, which is soluble, then you get, both those are aqueous, then you get sodium chloride, which is also soluble, it's just regular old table salt, and barium sulfate, which is insoluble. And barium sulfate can then be used, for example, if you drink something that has barium sulfate mixed in there, then the barium sulfate, it turns out, is opaque to X-rays. And it's a way to be able to X-ray image the digestive tract. Now, you may say, well, why don't we just do a suspension where we just take barium sulfate, which doesn't dissolve in the water, stir it up in there, and then just straight up drink it? Well, it's because barium itself is toxic, and there's a topic we're not going to get into called Le Chatelier's principle and the common ion effect. Technically, the common ion effect is related to, but isn't actually part of Le Chatelier's principle, but I like to think of it as such. And it turns out that nothing is truly insoluble, that it really is just things that we call insoluble are just very itsy little soluble, but barium, toxic, you don't want any of it dissolved. And it turns out that one way you can force it to undissolve, we talk about that principle where stuff that is undissolved, some bits of it will dissolve while other bits that are dissolved will undissolve, and you get that equilibrium there. Well, it turns out that the barium sulfate goes through, even though we call it insoluble, is ever so slightly soluble, and you get these little bit of barium ions in solution, and those are the real problem. Well, it turns out that if you really increase the sulfate concentration, then you can force this reaction to go backwards, and you can force more of the barium sulfate to be locked up as barium sulfate. And so this is why we would do this, is because we could really crank up the amount of sodium sulfate there. And then the sodium sulfate, that increased sulfate ion increases the sulfate ion that's in solution, because of course the sodium sulfate also dissolves. It is aqueous, but when it dissolves, it's a strong electrolyte, and so it breaks down completely into sodium ions and sulfate ions. Well, then those increased sulfate ions are what provides this increase down here that I've drawn in already and have redrawn there of the sulfate, which then shifts the reaction back this way and forces you to have undissolved barium sulfate. Well, undissolved barium sulfate your body can't process, and so it's going to pass out in your solid waste there. Story that goes along with this, and I know you don't really need it, but I kind of have experience with this. More, I should say, my family has experience with this. There is something called pyloric stenosis. And it usually happens in infants after they're born. One of the sphincters on the stomach, it's the bottom one, begins to thicken. It keeps growing, and it actually closes off the stomach, such that very little or no nutrients are getting digested and going from the stomach into the intestinal tract. And if the stomach gets overfull, then what happens is the child will vomit back out that stuff. And it is like Linda Blair in The Exorcist, just projectile vomit, go from one side of the room and hit the wall on the other side of the room, kind of just nasty vomit that the kids end up having. And pyloric stenosis is most common in firstborn males, firstborn sons. Well, that would be me and my family. I managed to avoid it, but somehow my sister, who is second born and of course a daughter, a female, she ended up with it. And it's so rare in females and in not the firstborns that the doctors, it wasn't even on their radar. And my mom got to where she just collected the data. And the doctors just thought that she was panicky, or maybe that the daughter was colicky, and they just thought my mom was a worrier. And so my mom collected the data of every day for a week my sister's weight, and she lost like 2 pounds in a week. And then in addition to that, my mom would measure how much fluid she fed her, started bottle feeding her, measured how much fluid she fed her, and then would catch that projectile vomit and pour it back into the bottle and measure how much she was getting back out. And it was pretty much everything, if not more, that she was getting back out. Took that data into the doctor and said, here's a week worth of data. And of course, the doctor could see the weight decrease, and they became concerned. Did this kind of X-ray imaging process, saw that sure enough, the barium sulfate mixture went down into her stomach, filled up in her stomach, and then they were able to see her projectile vomit it. And so they had to wait 24 hours and to guarantee her stomach was empty before they could actually do the surgery. And my sister still has a scar and won't wear two-piece swimwear usually because of that. She also has a scar from having to have her appendix removed, which is unfortunate for her and not related. I also have a nephew who ended up with this pyloric stenosis, and it's because of my family history of it that I was able to point out to my sister-in-law, hey, I think he might have this. You want to go ask the doctor about it? And she did, and they were able to get him in for surgery quick. I mean, just no questions asked. Yep, firstborn male, I'm sure that's what it is. I don't even think they went the route of imaging. They just saw the projectile vomiting and were like, yep, it's got to be that. They probably did do ultrasound or something, but it wasn't the same method to actually determine it. And then he was able to have surgery. In modern times, it's laparoscopic. He's not going to have any scars to speak of with that one as he grows up. So anyway, that's a long story, but there you go. Here we're getting into applying the solubility rules, which I mentioned in the prior slides that they in the last topic that they really didn't have us look at this. But here, because of the potassium, the alkali metal there makes this one soluble. Here, the nitrate makes this one soluble. Here, chlorides are normally soluble, but they're overridden when they're bonded to heavy metals like leads. That one's insoluble. Here we have the sodium ion. It also turns out the hydroxide ion is fairly soluble, but the sodium ion is what definitely makes that one soluble. And here, the aluminum itself is not soluble. In general, the phosphate is definitely insoluble, and so then the substance is insoluble. And that's just a table there of using some of the insolubility rules, and here we're going to have these as well. So here, this sulfide, usually insoluble, and when combined with the heavy metal, definitely insoluble. Iron sulfide, it's going to be the same way. We have a heavy metal bonded to a sulfide, so that's insoluble. As a side note, another example, actually, this asks why are they insoluble? So we know they're all insoluble, so we're going through why, but the fact that we have these solids floating around inside the liquid, that tells us that we've produced an insoluble compound. This one here is lead iodide. Well, its iodine is normally soluble, but when it's combined with the heavy metal ion, the lead there, it makes it insoluble, and you end up with the same thing here, that the hydroxide, I'd go as far as saying it's usually soluble, but when bonded with the heavy metal, that makes it insoluble. And so for all of these, the answer key says that no soluble ions whatsoever in these except for the iodine, but that is overridden by the lead. And so I don't know that I disagree or that I agree with them on the hydroxide being insoluble. Hydroxide can be soluble. Heck, the heavy metals can be soluble if they're bonded with a nitrate or an acetate ion, but in general, heavy metal ions insoluble, and so that's why we produce precipitates on all of those. These would be reactions where you took two soluble ions, something like cadmium nitrate, iron nitrate, lead nitrate, nickel nitrate, and then some kind of alkali metal bonded to the negative ion, something like sodium sulfide, sodium iodide, and sodium hydroxide. And so you start out with two things that are aqueous, and then we produce something that is aqueous, that we had a soluble ion here and here, let's say, and so then they end up combined over here. You know what, let's go ahead and make this a little bit clearer. And so the soluble ions end up combining over here, and then at least one part of this one is insoluble, if not both parts, and then that produces a solid that we call a precipitate. And this is a special case of double replacement. I mentioned back when we were covering chemical reactions that the most common type of double replacement is a precipitate. You also have some double replacements that produce gases, and you have double replacement reactions that produce that are acid-base neutralization reactions. But when we're talking with solutions here, a precipitate reaction is one of the most common ones we're interested in. Anyway, that finishes up section 3.